All right, whenever you have a charge, something like a point charge that's in the presence of an electric field, then that point charge is going to respond to the electric field and it's going to move. And how it moves, let's say we have an electric field that is constant and uniform in this region, and then I put a positive point charge right there. Well, that positive point charge is going to accelerate in the direction of the electric field. Now, if it had been a negative point charge, it would accelerate in the direction opposite of the electric field. So you can use that to make all sorts of electronic devices where you need to take a beam of charged particles and direct them. For example, let's say that we've got a plate with positive charge on it and another plate underneath it with negative charge. And that's going to create an electric field that will be constant and uniform except for fringing near the edges. If I have a positive point charge and that positive point charge is moving in that direction, it would normally go in a straight line, let's say something like that. But because of the presence of the electric field as it flies through that region, it's going to deflect. So it'll do something like that. Now, what this does, this allows you, if you have the ability to control this electric field, perhaps the magnitude and direction is something about this electric field that you can control, then you could control where the beam of charged particles ends up at. And that's the way an old school television set would work, is you would have not protons but electrons, a beam of electrons, and they would strike a fluorescent screen, a screen that when the charged particle strikes it, it fluoresces and creates light. Let's go and talk about what happens when you put a dipole in an electric field. So for this one, let's say that we've got electric field pointed to the right like that. And now we take a dipole. Remember what a dipole is. You have just as much positive charge as negative charge. And I'm just going to position the dipole like that. So we've got plus Q on this end, we've got minus Q on that end. Here's the center of the dipole. I'll mark that spot. Well, the fact that we are now in the presence of an electric field means that these charges are going to try to move. But they are bound together through the dipolar force, whatever's holding them together. So what's going to happen is the positive charge is going to want to move in that direction, and it's going to try to accelerate, so it's experiencing a force, the Coulombic force, trying to move in that direction. And the negative charge wants to move in that direction, and that is going to be also the same force as what is on the positive charge up there. Now, you'll see that those two forces are in opposite directions. That indicates that those two forces are going to cancel each other. So there is net force. There is a net force of 0 acting upon the dipole when it's in the electric field. However, there is something that's going to happen here, and that is that this dipole is going to rotate. So it experiences a torque. And even though the net force is 0, the net torque is not 0. I think you can imagine what's going to happen here. If this represents the dipole, it's going to rotate this way, and perhaps it'll do a little bit of jiggling back and forth until it settles down and reaches equilibrium, where the dipolar axis is lined up with the electric field lines. And at that point, it's in a state of equilibrium, so there won't be probably no more torque that's going to act upon it unless something changes, unless the electric field changes or something else changes. So let's figure out what that torque is. You probably recall from your mechanics class that torque, which is symbolized with the small Greek letter tau, is equal to R cross F. Now those are forces, so that makes torque a force. So we have the cross product here. Now the cross product, hopefully you're familiar with that, uses the right-hand rule. R, in this case, is the axis, the distance from the axis of rotation. So in this case, R would be the distance from here to the point charge. So that represents the distance R. Now, previously when we were talking about a dipole, we called this entire distance from here to here D. So D, that's D over 2, is going to be what R is for the top particle. And then we're also going to have D over 2 down here, but since it's in the negative direction, and remember we're treating this like it's a vector, then that would be negative D over 2. So let's call positive towards the positive charge, let's call the negative direction towards the negative charge, like that. And I suppose technically if we're going to treat these as forces, that we'll call that one the positive force in the positive direction. This is the same force, but it's in the negative direction, like that. Okay, so to figure out the torque here, what we need to do is plug in for those variables. Now, magnitude of the torque, you can figure out this way. Magnitude of the torque is going to be the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. So in this case, one vector points this way, F points that way, so if we extend that on through, this right here would be the angle between the two vectors. And you can imagine that that angle is going to change as this thing rotates. Now, the direction, that has to do with the magnitude of the torque. The direction of the torque is going to be into the page. Now, why is that? Well, take your right hand, put your now there's lots of ways to do the right hand rule. You know, there's the finger method like this, where you've got 3 fingers and you know they're always going to be perpendicular to each other. Here's my method. It's just the way that I learned. Maybe yours method that you know works better for you, but for me, I put my hand, all of my fingers, in the direction of the first vector. So if I put my fingers like that, that's pointing in the direction of the first vector. And then I cross my fingers in the direction of the second vector. So the second vector is F, going that way. So in order for me to bend my fingers, you know, my fingers will only bend in one direction, like that. I need to rotate my hand over like this. So fingers in the direction of the first vector, bend in the direction of the second vector, and now my thumb, which points downward, is pointing in the direction of the torque. So the torque, the vector torque, is into the paper for this top vector. Okay, let's check it for the bottom vector. Well, I put my fingers in the direction of the first vector. That's downward here. This right here would be the vector from the center down. And then I bend my fingers in the direction of the second vector. In order to do that, I have to turn my hand over, bend like that. It's kind of difficult to do like this. But once I do that, you'll see my thumb is pointing into the paper also. So both of these torques are going to create the same direction of torque. They're not opposing each other. So the grand total of the total torque is going to be into the paper. Now that creates a clockwise motion here, and the magnitudes are just going to add for those two then. So the magnitude of the total torque, and let's just write total on this, is going to be, okay, the magnitude of the first vector, that's D over 2, times the magnitude of the second vector, that's F, times the sine of the angle between the two, which we'll just call phi at this point. All right, that's the first torque. Now I need to add to that the second one. The second one, the directions are different, so I've got to be careful with my directions. D over 2, but it's in the negative direction. So there's the first vector. And then F is also negative, so that's the second vector, times the sine of the angle between the two, like that. Now we can recognize that those two angles are going to be the same because they're measured between the two vectors. So whatever that angle is there, it's going to be the same angle phi down here for that. So those two angles are the same. That means I can combine these together, and you'll notice the negative signs cancel each other, and I end up with 2 times d over 2 times f times sine. So let's just get rid of that 2. This is going to be d times f times the sine of phi. All right? Now, the force in this case is due to the electric field. And we know that the electric field is defined as force per charge. So the force itself is going to be E times Q. So we can rewrite this as D, and this F becomes Q times E times the sine of phi. Also recall that Q times D, we've already talked about how that is the electric dipole moment. So this is P times E times the sine of the angle between these two. Now, you know that P is a vector. You know that E is a vector. The direction of P is always from the negative to the positive charge. When we talked about the dipole, that's one of the things we learned. So this is actually, you can think of that as a cross product itself. Magnitude of the first vector, magnitude of the second vector, times the sine of the angle between the two. So we can take this torque, and now we can express it really in vector notation as a cross product of the p vector and the e vector. So there we have an equation that describes now the torque of an electric dipole in the presence of an external electric field then. Okay, moving on. Let's take that dipole, and you can imagine when it's in that electric field that there's going to be some potential energy associated with its rotation. So if you'll think about it being maybe straight up and down like that there, this is going to have more potential energy in the system than it would be if it were positioned like that. If it's positioned like that, that's pretty much the equilibrium position. Unless it's rotating through that and bouncing back and forth, oscillating, heading towards its equilibrium, then that is the equilibrium position. So you can see there is stored energy in that position. In other words, to go from this to this requires you to come along here and literally twist the dipole and put it in that position. So energy has to go into the system in order to go from here to there. All right? So that's another way of saying that potential energy is stored in the system when it's in this position here. And the same would be true if you went even farther. When you go back like this, there's also energy stored in the system. And that is technically an equilibrium position, but it's an unstable equilibrium position, because if it gets off just a little bit, let's say there's the center of the rotation, so if it moves just a tiny bit to one side, then it's going to snap around and try to head towards this equilibrium position. All right, well, U is the symbol used for energy in this case, and you know that energy is the negative of the amount of work required. So, you know, that's another way of saying, well, if I do the work, then the system gains energy. So I'm losing energy, that's the negative. The system is gaining energy, that's the positive. That is similar to, and another equation that you know is that the integral of the force over some distance is equal to the amount of energy, that's work. Okay, so that is for a translational force. It also can be changed for a rotational force And what is a rotational force? Well, that's nothing but a torque. So if we include torque d theta, then this will also tell us the amount of work. All right. Now, if you take this torque that we had previously here, and you work with it and you plug it into here and you integrate it, then you're going to end up, we're not going to do this integration, but you're going to end up with U equals minus P E times the cosine of the angle. Now, you can work through that and see that that is indeed the case. It's not difficult to do that. You'll end up with this. Now, if you'll look at this, this is a dot product. If you take that negative sign, leave it there, but P dot E, if I take the dot product of these two vectors, then that's the magnitude of the first vector multiplied by the magnitude of the second vector times the cosine of the angle between the two vectors. So now we have an equation for the potential energy that is stored in the dipole that's in this external electric field. And you can see, since it's that cosine term stays there, that the amount of stored energy is related to this position. So as it goes from this position, from this rotation to this rotation, it's gaining energy, okay? And this way as well. So we have two equations now. This one for the amount of energy stored in the dipole, and this one for the force, the rotational force, which is the torque on the electric dipole. So we've got those two equations right there. All right, let's take that information and let's see if we can put it all together and solve a problem. Suppose that we have a water molecule, and the water molecule has a certain separation between the modeled plus and minus charge. So, we're going to treat it like it's a dipole. So there's the positive, there's the negative, and there's this distance d between the two. Well, what we want to do is we want to find the d. We want to discover what d is. And maybe we can figure out what the torque is, maybe the maximum torque, what is the work required to turn it from one angle to another angle, something like that. But we have a dipole, and we know that it is a dipole in an external electric field. And for the sake of this problem, we'll define the electric field as a constant. And let's make it a nice round 1.5 times 10 to the fourth newtons per coulomb. So it's a constant value. We know that this is going to be a water molecule. So you can go look up the dipole moment for a water molecule. And it is 6.2 times 10 to the negative 30th coulomb meters. Okay, so these are the given things. We also know that because it's a water molecule, it's composed of H2O. So 2 hydrogens and 1 oxygen. Well, if you break that molecule down, you know that there's 2 hydrogens. That's going to give us a Z of 2. Z is just a number of charges, number of protons. So it has a Z of 2. Not that hydrogen has 2, but each hydrogen has 1 proton, but we have 2 of those, so that's why it's 2. And then the oxygen is going to have a Z of 8. So it's going to give us a charge of 8. So that's a grand total of 10 charges. Now the way to translate that into the model over here is that we have plus 10E at the top and minus 10E at the bottom. So there is our water molecule modeled right there. Okay, well, since we've got P and E, we should be able to figure out what D is pretty quickly, because remember what P is. P is Q times D, where D is the separation between the two. Now, Q is going to be this 10E. So you have plus Q on top, minus Q on bottom. The net charge is 0, but that's not the net charge. That's just the charge on one of those ends of the dipole. And we can plug in, well, we're after D, so D is going to be P divided by Q. We can plug in the numbers for that. 6.2 times 10 to the negative 30 coulomb meters. Divide that by Q. And the Q is 10 times E. And what's E? Hopefully you remember that. 1.6 times 10 to the minus 19 coulombs. All right, you should be able to do that calculation now. And here's what I got. 3.9 times 10 to the negative 12. Now what's the unit going to be? Well, the coulombs will cancel. We're left with meters. So D is given as that right there. Okay, we can figure out torque here as well. Let's go ahead and do that. The torque equation, that's going to be given by this. So it's going to be P cross E. And if I just am interested in the magnitude of the torque, because I'm not, for this problem, I'm not given any kind of directions for E or angles between the two. I'm not given that. So the magnitude is going to be PE times the sine of the angle between the two vectors. But because I'm not given that information, I really don't know what phi is here. But what I can figure out is what is the max torque going to be. The max will occur whenever this angle here is 90 degrees, because at that point the sine is going to be 1. All right, so the max is just P times E. So if I plug in the numbers for that, P is 6.2 times 10 to the negative 30th, and coulomb meters times E, which is 1.5 times 10 to the 4th Newton per coulomb. That turns out to be, what does that turn out to be? 9.3 times 10 to the negative 26 Newton meters. So that's the max torque for this problem. All right, we can also figure out the amount of work required to flip it from some angle to another angle. Let's say the amount of work, we'll call that negative W, and that's equal to U final minus U initial. And U final, let's say, is at 180 degrees minus U initial, which we'll say is 0 degrees. So we're flipping this thing over from 0 degrees all the way around to 180 degrees. And how much work is required to do that? Well, this is pretty straightforward. You know what U is. U is given by this equation here. So the magnitude is going to be this. And we're given the angles here. So we should be able to plug those in. That's going to be minus PE times the cosine of 180 degrees minus negative PE cosine of 0 degrees. Well, cosine of 180, that's negative 1, so this becomes minus 1. This becomes positive 1. So we're left with, and remember these are going to cancel each other, so when you sum those up, we're going to have 2PE, like that. Okay, now the magnitude of PE we already figured out up here. PE, that's the max torque, happens to be the max torque. So we've already got that numeric value right here. We just multiply it by 2, and there's our answer. That's how much energy is required to flip it around. I'll leave it up to you to do that calculation, but it's going to be 2 times that right there. Okay. We're getting ready to move on to a different topic, and we'll talk about Gauss's law in the next video.